guess it's still morning. So good morning, everyone. And thank you for coming to my presentation. The title is quite broad. It's a little bit of a, maybe Christmas carol. I wanted to give something broad, but then as I worked on it, I certainly adhered to the original structure, but you'll see that there's some other things that came up along the way, and so I couldn't change the original title and all. But all the keywords in that presentation and description title will be covered. So a lot of times I like to start presentations with this quote from a book that you can see the title there. It's on FPGAs for software engineers. And that programmable part kind of throws people off sometimes. So you got someone says like, hey, FPGAs, right? This software person. And then the hardware person says, it's the other way around. The hardware person says FPGAs and the software person says what? And then they say field programmable gate arrays. These are cool programmable chips. And the software person says programmable. I could do that. And it's, a little bit of an asterisk there. So what we're going to look at, we see here the agenda. I'm going to do some introductions. We'll want to sort of the obligatory FPGA background slides, just to sort of frame things. We'll talk a little bit about the NI FPGA platform, workflows, right? How it's used, a couple of case studies, and then future trends, right? No one has a crystal ball, nor do I. And you'll see there's a certain structure that I took to come up with the trends that I'm proposing here or suggesting. Okay, so maybe show of hands. Who here has heard of FPGAs? Okay, that's good. No idea what an FPGA is? Oh, okay, maybe it's like one person, they're afraid to raise their hands. Who uses FPGAs in their work? Okay, that's good. Well, anybody who doesn't use FPGAs, wants to use them? Okay, 2 people. Anyone doesn't want to use an FPGA? Okay, I put that in there as a, tease a few of you. Well, thank you. Thank you for coming. That's quite bold. About me, I have an electrical engineering background. I've been using LabVIEW for my entire career. I picked up LabVIEW FPGA. I don't count the years anymore. I just look at when I started, kind of like a car, right? And then in 2020, I wrote a book on LabVIEW FPGA. One thing to note is all the EW, the radar stuff, they added that on there, just to make it more application specific. But I've worked in a lot of different other areas, right? Sometimes people think I'm like some kind of radar expert, but I wouldn't say that, right? I kind of know how to use the FPGAs in a lot of these different places. I would say that and I've worked on projects where I've trained people, I've consulted them, I've managed projects. I've done development in architectures of FPGAs. So I've kind of seen it from many different angles. And if I would sort of summarize, where am I now? I would say I'm a big fan of a systems engineering approach. Anyone here use systems engineering in their work? Oh, 2 hands, okay. Okay, you'll see what that means. We will see how it applies in the presentation. Okay, so FPGAs, why and what? So, if you don't want to use an FPGA or you want to use an FPGA, I think there's a lot of challenges and risks associated with using an FPGA. So it's really important to upfront know, why are we using it? As an example, if you see a project where they're using an FPGA and you can't answer that question, you're probably going to be spending a lot of money and time with an unknown output. So we have determinism. An FPGA is a hardware device. And so that allows for low jitter, very low jitter. Everything has jitter, by the way, right? Temperature can affect jitter. Then we have low latency. So we can have a quick response to some kind of we can make a quick output response based on some kind of an input or some kind of an event or a signal. And typically we're talking microseconds. Could be faster than that. So that's one thing. And then high throughput. So we have large amounts of data. What do we mean by large amounts of data? Imagine you have an NI PXI chassis full of cards, and each of the cards has 16 channels, and each channel can acquire 50 million samples per second. Each sample is 2 bytes. We'll do the math on that, and it's over a gigabyte of data per card times 17 cards. I don't think computers can handle that. So the throughput part is a critical part of FPGAs where they can consume that large amount of data. The last term that I have there is FPGAs go wide. So I like to use the auto analogy here, right? I can have 1 lane of traffic, and then I'm not going to make the speed limit 200 miles an hour, right? We're going to keep it safe. We can add more lanes, and those more lanes increase the throughput. We can now have more cars, more traffic, more people driving on that road. So that's how FPGAs handle high throughput when we talk about gigabytes and terabytes per second. And then we have custom hardware. Seems to be a bit of a catch-all, but there's companies that have obsolete hardware. You can't find the components for it, and sometimes it's not even that complicated in this last one. Maybe it's something that's proprietary, or it's something that they don't want to be able to go to like an outside, a contractor or a vendor and say, hey, build this for me. Or it's so specific that the market just doesn't want to make something for that use. So that's the last why we would use an FPGA. So now, what are FPGAs, right? So it is an acronym. We did mention that. Some terms that you'll see out there, you'll hear the term like software-defined radio, software-defined networking, software-defined X, software-defined something. So if you hear that, typically there's an FPGA in there. They have no operating system. And you think of it as a configurable integrated circuit. We'll expand on that. And then we can see here that they're programmed with a specific type of language, right? Because it's hardware, because there's clocks, because there's various resources, timing, and so forth. General purpose language like C, for example, won't work with this out of the box. So here we see like a super simplified view of what an FPGA looks like. So on the outside, we have the I/O blocks, and traditionally FPGAs are digital, right? You have digital I/O on the outside. Within the FPGA, we have what are called configurable logic blocks, and that's a simplification as well. People think of it as just gates, but as semiconductor technology has advanced, that has become more complex. Those gates were combined to create lookup tables and to create DSP, digital signal processing blocks. Memory goes in there, to the point where the manufacturers will even hard code or build into the FPGA specific types of IP or intellectual property. So for example, a lot of these chips are interfacing to PCI Express. So they'll just build that right in. When they build it in, it's a lot more efficient than us building it. Other things that they've added are whole CPUs have gone in here. GPUs go in here. And then with AI and ML, right, they're starting to put cores that will, we say the word cores and IP, those are terms that we use in the FPGA world. You'll see that they're putting things that satisfy a certain application or market need. So when I said there's no operating system, we could have an operating system. If we put a CPU on here, that CPU could then have an operating system. Now, this is very technical, but if we take a step back, one way to think of FPGAs is to compare them to other things that we know about. We know CPUs, typically. We've heard of GPUs. Some of us may have heard of ASICs. And so here I just do a very sort of general comparison of FPGAs to some of the other types of integrated circuits that are out there. Notice some common things, right? Latency is kind of the same with FPGAs and ASICs, right? They're both hardware devices. Throughput, we have high throughput on everything except for the CPU. And again, these are really relative terms. We're trying to just get a sense conceptually. The devil's in the details. You'd want to look at the specifications of the specific product that you're using. Development time. I think I didn't want to add a fourth level, So that's where development time I've got medium and medium on GPU. FPGA would probably be higher than that, but I didn't want to call it high because high was reserved for ASICs. So now in the software world, we think of FPGAs as really slow, right? Like we got these overnight compiles and these issues that they're big headaches. But if you compare them to ASICs, FPGAs are in fact fast in terms of development. To spin up an ASIC, we're talking months. So, I don't know, overnight compared to months is really fast. I mean, it's quite amazing. So that's how we, comparatively, we have the FPGA being, it is a rapid hardware development tool. And we are developing hardware, it's not software. So that's, in the CPU and GPU world, we're writing software. So we kind of skip down to the bottom, right, developer skill. We see that the skill is primarily hardware for the FPGA and for the ASIC. And then we see that for the CPU and GPU, it's a software skill that's needed. Of course, for the GPU, if you're running things in parallel, you do need to be aware of parallelism, how to apply, how to unroll your algorithm and things like that. Yeah, the reconfigurability is a highlight of the FPGA, right? Once you've made that ASIC, you've spent 18 months, that's it, you're stuck with it. If you want to make a change. But with the FPGA, you could change that. Again, it's overnight, but it's a lot faster than 18 months or 12 months. We see the custom hardware as well. Now, this here are challenges at large. It's not just NI or Intel or AMD or specific manufacturer. So it's a very specialized skill set that's needed. So electrical engineers with a really, a specialized electrical engineer typically is working with an FPGA. It's very different than software development, right? The software developer will say, how do I do, can I do mutexes? Can I have threads on an FPGA? It's like, nope, those don't even apply. Or you tell them about synthesis, and they're like, what's synthesis? The compile times are really long, right? Software used to have long compile times. I wasn't around for that, but people had punch cards and they'd have the compiles would take overnight. That problem's been solved. But with FPGAs, it takes a long time to get a compile. So depending on the hardware, it could be, you can see here, it can take a very long time. It could still be, even minutes is a long time. The key challenge there is that it breaks the workflow, right? Like you're in the zone, you're in the mindset, you're doing something, and then I gotta go do a compile. And that's mitigated with a simulation. So simulation is what everyone who's using FPGAs uses to mitigate that, to test out the algorithm, find bugs before waiting all that time to compile something. And then the fourth one, we've got vendor lock-in. And again, this is a broad statement because the tools themselves, they sort of want to protect their, and again, this isn't just like an NI thing, right? This is all around. They do want to protect their market share, their users. And so there really is, and there's a really good YouTube video that talks about, maturity of it and why, sort of goes into that. And generally my observation is that, we talk about software, you go to any of these other software classes or sessions here, you'll hear people talk about things like source code control, CI/CD. In the FPGA world, I think it's, at least in my view, it's slow. It hasn't picked up yet as much as, especially when compared to software. Typically, for example, it's like one person. Like you have like a team, a firmware team, but maybe there's like one person that's really just doing the main part of the FPGA. Like that's the person that's doing that. That's the context of that. And because there's just one person, you don't really need to have a lot of like tools and practices to, get people to work together. Okay, so now let's talk a little bit about the NI FPGA platform. So generally we have our decision, our calculation happening in the CPU. And there's a lot of latency, there's a lot of time that's lost going to, we get ease of use. It's simpler to program if it's there because we've got an operating system and a driver API that can help us with that, with the software. But in some cases, we want to be able to bring that calculation down to the hardware. So NI has a kind of a broad, different set of hardware that uses FPGAs, and that's too much to talk about in one session. And that's not really my goal here anyway. But we'll just show you a few, just to give you a sense, right? You've got these cards, and they've got an FPGA on there. They plug into a chassis. They've got memory, they've got I/O, different kinds of I/O. So these are, a lot of these are analog, I guess. And then here we've got like high-speed serial. So this is where we can just move large amounts of data in and out of the FPGA for processing and the other way around. So the overall idea is, I move quickly through those because you can just go online and read them, right? I don't want to take your time for that. So the overall idea is we want to be able to focus on what's unique about our project, right? Plugging it into a chassis is not unique, right? That's the whole bunch of cards that do that. Interfacing to some kind of memory or DRAM, that's not really that unique. But if I have some kind of code or logic that I want to put in and write it using LabVIEW FPGA, I can do that. I could also integrate user VHDL if I have some IP that I want to bring in and integrate. And then, of course, there's the different I/O interfaces, right? So it's kind of like an interface diagram that shows kind of like the world of someone who's working with an NI FPGA card. So LabVIEW FPGA is it's an add-on, right? You install LabVIEW and then you have LabVIEW FPGA installed with it. It's been around for a while. It's turned 21, I guess, right? And it works on top of, we say Xilinx, right? Xilinx was bought by AMD. So you'll see me using them interchangeably. Xilinx doesn't really exist anymore, but we all still say Xilinx. So it works with Vivado. Vivado is the development environment that AMD Xilinx makes for their FPGAs. So the LabVIEW FPGA part kind of works on top of that to generate the bit stream. Now, one of the things that you may see in the case studies and some of the things we'll talk about later is we want to be able to verify we've got some kind of I'm just going to show all the parts of this. The idea here is down here at the bottom I've got some kind of a model, right? I've got some kind of IP that I want to put into hardware, and typically what we'll do is we'll first model it, right? We'll write it and say in some kind of software language, as you can see here, and we'll kind of figure out the details of it, how is it supposed to work, the data types, the computing, and so forth. And we'll have some kind of test vectors that go through that, and then we can look at those results. So it's kind of like this, we'll have this bottom piece typically developed first, and then the top piece is where the FPGA part will go. So the idea is that those could be sort of swapped out. So you could test out the model, the same data should be able to go into the model, and give you some kind of results, and the same data should be able to go into the FPGA and then give you the same result. Now in the FPGA world, they've been doing this for some time. These days, this is referred to as model-based system. I tread lightly when I use the term MBSE, because I'm not an expert in that, but it's close to what's called model-based systems engineering. And the bottom piece is what we would call our digital twin. And so, for example, let's say this has all been built, and I want to go and change, a requirement changes. I can first run it on the model, confirm it, test it out. First of all, confirm the requirement. What if they give you a requirement that's not achievable? Or we don't know the math for it? We shouldn't be in the FPGA just yet. Now, one thing about LabVIEW being graphical, it does, the spatial aspect of it maps pretty well. Now, this is not a literal mapping of it. The tools sometimes will optimize and find where that best happens. And trouble with this slide, it's a common one that you'll see, is, people say, look at that and say, it's easy, right? Well, easy, let's really be careful about that. So we've got a couple of slides here to just show you, just what that environment looks like, right? We've got our I/O and we've got our DSP. It's a very familiar environment. Those of you that have worked with LabVIEW, we have access to our I/O. We have timing through our loops. There's a bunch of functions that come with the LabVIEW FPGA development environment. And so those are kind of like higher level, easier to use, maybe less control, right? That goes hand in hand with higher level. But if we want to, Xilinx, AMD, makes IP blocks, function blocks that work just on their hardware. And some of those are either, they're not free, They're part of the purchase of the hardware. So we have paid for them. But they're available to users. Some of them are licensed. So it's kind of like, you can buy different kinds of functions, right? So you don't need to build everything from scratch. And so LabVIEW FPGA gives you, I just put give you a sense of like the types of functions. And then if you were to use one of them, say like the FIR compiler, who doesn't need a filter? We have, this is, when you put one of these blocks down, you'll see that there's the same wizard that you would use in Vivado comes up, and you're able to sort of click through and configure it just as if you were using the Vivado environment. So like NI is not rebuilding that part. It's all sort of like part of it. Yeah, and you can just see there's things there, right? So again, we kind of talked about different ways that we can program it. Now, if that's not enough, and you have your own VHDL, they give you different ways. We have the IP integration node. We have what's called the clip. So there's two general mechanisms of integrating IP into LabVIEW FPGA, so we could use that, right? So if it's already been written, or maybe we wanted to optimize it a bit, or maybe it's based on the expertise that we have in-house. Right? So there's a number of reasons why this is a good option. But again, we're just kind of going through all the different approaches. There's a table that's in the LabVIEW help that breaks down the differences between clip and IP integration node. I've seen on projects, typically, especially when I'm consulting, I've seen projects where they choose one or the other, and I don't think they really thought it through. And in the end, they add cost to that effort or that project. So I think it's really important to take a hard look at the two approaches. My simplified view of it is with the clip, you have more clocks, you have more ability, more freedom is given to the IP designer. With the IP integration node, it's more limited and it's in line to the LabVIEW FPGA block diagram. But for me, as someone who's typically working on the LabVIEW FPGA side, you'll see that we do have support for simulation when it's integrated into LabVIEW FPGA. That to me, project's not just about me, right? It's the whole project. But from my point of view, I like it because of that. But again, sometimes you also want to be able to give more freedom to the IP developer. So again, this is a generalization of I'm giving you the general point of view, like some general insights, but you certainly want to consult the help on this. Now the compiling process, our code is, we write our LabVIEW FPGA code, and then the LabVIEW FPGA side will turn that into essentially like a Vivado project, which has VHDL and all the files that are needed for that board. So these are at a high level, some of the steps that happen when we're creating a bit file. Okay. A couple of years ago, I introduced something that was, it's really tricky because you can add more features to LabVIEW FPGA, but at the same time, you've got companies like Xilinx, AMD adding features to Vivado. So, it's a tricky thing because they don't want to just be in competition with it, right? They want to be able to add some value, but sometimes, there's some features they will never have on the LabVIEW FPGA side or on the higher level tools because it's a higher level tool. But let's say you want to work directly in the environment of the manufacturer. They have a feature called Vivado Project Export. And in your LabVIEW project, this is a compile option. It's not available for all the targets, or maybe it is. A lot of the newer projects do support it, the targets. And so that allows you to create this export. And that creates, it just creates like a new folder, and then everything is put in there, and then you can work within the Vivado environment. So all those abilities, like, plugins that you may have, or lower level, whatever it is, there's some tweaks that you want to be able to make. This gives you that access. So just a quick sort of summary of that. So they give us this, there's some board support IP, right? We can't just put anything in there, right? Because the board after it's built, it has I/O, it has interfaces in specific places. So we can't just put anything anywhere. The user clip, like the clip, remember, is a way of integrating our IP into LabVIEW FPGA. So that's the part that we're going to add in there. But we put that in there almost as a stub. Because what happens is with Vivado export, NI encrypts a lot of their stuff. So this forces a part that will not be encrypted. So then that's the part that we can essentially define the interface. And then once it's exported, right, we do the export. And now we're in Vivado. That part remains open and not encrypted, so you can work within that part. And I want to say this has been around for at least 5 years, so it's gotten use. And then, of course, when you're targeting in this workflow, we're targeting the same card that we originally started out with. So like the same NI card that we started with, we go export to Vivado, and then we compile, and then that bit file that we make in Vivado can only work, it's for that specific product. There's one more. A couple years ago, I introduced something called the LabVIEW FPGA IP export utility. So this here allows you to export the LabVIEW FPGA code that you've written to run on a non-NI platform. You can see when it started, 2020. Now, there's a couple of things that aren't supported, and quite frankly, I don't think we would want to export them. Again, I'm not trying to push a point of view there, but there's a couple of things like DMA FIFOs, peer-to-peer, DRAM, some of the I/O interrupts. There's a couple of things that aren't supported by this. And if we think about it, if I'm writing something, I'm prototyping, doing some rapid development on the NI FPGA platform, and I want to use it on some product or somewhere else, the interface of that device is probably not going to be the same it won't be the same as the NI one. First of all, NI probably doesn't tell you everything about like the interface of it. It's sort of packaged up. And you want the freedom to be able to make that part. So you want to make the IP as portable as possible. So that it's really the key thing is in defining that interface. So they give us two options. One is netlist, and the other one is with just VHDL. And it's not too different than typical workflow, just that we're adding on, I guess, number 3 is where we start with this particular workflow. Right? We do our development in LabVIEW FPGA. We can simulate in LabVIEW FPGA. We do all the things. We can even do hardware tests and some other things. And then so at number 3, you see that's where we sort of export, and then we have that, and then it's an IP block that we're then integrating into our project, just like any other IP that we talked about, or that you could have made. Okay. Some considerations. You do need to target the same target family, right? So, for example, it's like Kintex UltraScale or UltraScale Plus, Vertex UltraScale Plus, right? There's a specific family, like the way they categorize things on the AMD Xilinx side. You have to fit within that. So that is a caveat. Okay, so now we're kind of about to go into the case studies part. And some of the things that I showed, maybe you can find them online. Maybe I'm providing some insights. But I want to give some observations of mine. So there's strengths and weaknesses. And one of the things we've seen LabVIEW FPGA can do is it allows domain experts. Domain experts is a way of saying people who are not programmers. But we don't call them that, right? Because they're maybe like RF experts, or they're imaging experts, or AI experts, something. Someone with LabVIEW skill, that skill gets expanded into that. But of course, they do need to learn some hardware. That graphical aspect of LabVIEW does play well. I mean, if you look at some of the other vendors, you see that they are making more graphical tools for their FPGA development environment. So I think LabVIEW FPGA was ahead of that, back when it first started. The fourth bullet over there, some skill portability across I say some skill portability because if you worked on, like, say, Compact Rio or an R series card or a Flex Rio, there's definitely some commonality, a lot of similar things, but then there's also things that are really specific about that hardware. It's not as portable as, say, going from like LabVIEW for Linux, from like one OS to another. It's definitely you need to sort of understand the differences. And sometimes they can be really big, depending on the size or the application. Peer-to-peer to me is, I know it's sounds like a lower level thing, but I think that is a strength. The fact that I can actually, with ease, I can move data between one FPGA card to another, and even with some of the NI instruments. But to me, that's a really key feature. And specialized and diverse applications. So NI is kind of like making these tools, right? And people can take them and build different things. It's really interesting to see the things people have done with that. So what are some of the weaknesses? Just again, observations. It's hard to tell if it's a function of the FPGA itself or the development or the types of applications, but it's hard to see if there's the community has hit that critical mass. Like you see kind of like on the LabVIEW side, you see, or you go to other environments, you see this more stronger user base. And maybe it's because training is challenging. I've taught a lot of classes in LabVIEW FPGA, and for me, I always break it down into 3 areas. I always want to understand the user's background. Is it a software person? Is it a hardware person? Is it an algorithms person who may be a software person? I want to know the FPGA product that they're using, and I want to know their application as much as they can share. So those 3 things, at a minimum, make a uniqueness to a specific way that the training is delivered. And that is challenging, right? Because you can't make 100 classes for everyone to be, to fit everybody. So they all end up having a lot of customization happens there in the training. It is primarily for NI FPGA hardware. And, of course, with the little caveat there of, IP export does allow us to go onto other hardware, but that's primarily. There's no system on chip support. There was some, it's sort of, it's just not there. And then the last one, some solutions can have high complexity. Let me just expand on that because it's just a bullet there. You start out with LabVIEW FPGA, you put a PID, you put a filter, you're like, hey, this is cool, I'm doing things, I'm making hardware. Then all of a sudden someone's like, well, we want to have 5 or 6 of these things and lots of cards and working together. That gets really complex. That's not, right? Remember, easy, right? Profanity. We have to be really careful about how that's thought about. And so that will get complicated. It can get complicated. It's almost like this hockey stick of complexity. Sort of grows and grows, and then at some point it's almost like you're building hardware. Now, I don't know how to compare that to how if that same larger application was built purely in Vivado, but certainly, I can certainly cite that here. As it gets more complex, you do need to have more and more knowledge of the hardware behind the scenes. So that is a key point as well. What I have found in my experiences is, you learn as much as you need for the project, and then you're always learning more and more about hardware. But to know all the things that the digital designers know, if you're just doing LabVIEW FPGA, it's near impossible, right? It's such a specialty. So now we're going to go on to the case studies. So these are from projects that I've actually worked on. Because we have a limited time, what I did was I took a sort of a slice of that project, sort of like a view, of a cross-section, right? Like a specific part of that project that I thought you would be interested in. And I give you sort of my insights and what I observed, what happened. So the first one is a reconfigurable IQ digitizer. So it's an NI card, and it's processing. IQ is a type of RF data. Now, I talked in the beginning in my introduction. I talked about how I'm a fan of systems engineering. Every project really should start with this, and should always maintain something like this and other diagrams. We shouldn't just be in the code. I know that people like to go to presentations and see someone open up code and start changing code and things like that. I like to kind of talk about this part. And I know this is kind of high level, but it is good to capture the complexity of that particular system. And our FPGA, in this case, is going to be where it says hardware, kind of on the next to that TDMS files. I think it's important to notice all these things because things that I do why is this important? Because things that I do in the hardware, in the FPGA itself, that simple decision, it could affect everything. And I should be doing it with some kind of knowledge of the system. Maybe I don't need to know the whole system, but someone has derived those needs and requirements and brought them down to me at the hardware level. And then vice versa, right? Things I discover, what's possible in the hardware gets pushed up to the designer level, the system level. So first thing that we saw with this, and there's a supporting diagram after this one, right? I just wanted to give you some high level. So they had wanted to put some kind of DSP blocks into this FPGA. And they sort of understood, you can go read the data sheet, like those filters or FFTs, right? They can go in and read about what those things do. But they wanted to know kind of like what the trade-offs were, because they have a lot of settings. So they wanted to understand how that will work in the system. So you may have heard of star, right? So I kind of used a subset of that just to break down my thinking, apply some, decompose the thoughts into things that hopefully you can more easily consume. So what we did for this was we developed a template that allowed us to study and review each of the DSP components. And same with the customer, right? They could also take that and review it and see exactly what we're seeing. They could put their own signals into it, and they had that flexibility. And then the result is that now they have this standalone software that they can then try multiple developers at the same time, right? It's not just one person. And they can even try different models, right? So we used a good amount of object-oriented programming in building this. And what's another key outcome is DSP IP integration risk was reduced, right? If I'm just trying to throw it all into the FPGA and wait those long compile times just to see that something, I could have studied in a much simpler environment. So let's see if we can zoom on some of these. So yeah, here we see in the blue is where we identified modules. And then we see there's different clock rates. And I know it's common to say, well, LabVIEW is graphical, right? Let's just do that there. We in fact start, before we even jump into LabVIEW, we do this. So this allows us to understand the general flow. And of course, I've removed the specifics of the project, but you can sort of see data's coming in at the upper left. It's getting processed, things are happening. Then we can run at a different clock rate. Those boxes are the clock rates. And so this helps us understand it without getting into LabVIEW. And I know LabVIEW is high level, but I don't want my customer to have to load LabVIEW to be able to see what I'm thinking. Maybe later on, but at least in the beginning, I want them to be able to just see the things that are critical to the design. Because there are things that are in LabVIEW that are just really syntactual. Like these are just like handshaking, for example. Like does the designer, does the customer need to see all the things that, we're gonna do those anyway. That's not a design decision to use handshaking, for example, or pipelining. That's not like, it's not what we're debating. So you see here that we identified in this project some places, wherever it says module, those are the things that we identified as things that we want to study on their own. There are things that could be reused in other projects. I know it's tricky to know what you're going to reuse on just one project, but those were identified, we made decisions and said, these are things that could be reused in other projects. So the graphical view of the action, kind of like that other diagram that you saw earlier, right? We have these, we send things through a model, and then we can also send the same thing through an FPGA. And we made a framework that supported that. And then this shows we made it so that we can have different classes for, it's a class-based architecture, right? So this allows us to have different models, right? Because if I have this IP that I want to develop, maybe I have different models that I want to be able to send in, right? It's not just one. Maybe we're trying different ones. And then I want to be able to have different FPGA implementations. And then I want to have different, not just FPGA implementations, but also different simulated FPGA implementations, right? The simulated sometimes runs a little differently. It's the same IP, but it runs differently because it's running a lot slower. So I want to be able to have, I just wanted to have a separate child class for the simulated part of the FPGA versus the FPGA itself. Like number of samples that you send in, timeouts, all those things are, samples are smaller, timeouts are bigger. So we wanted to just kind of like abstract that away so that way when it's running in simulation, it has that flexibility. And I think what I've seen is whenever I show this to others, it's a pretty common thing. I don't think this is unique, what we've developed here. You know, it's common that a lot of development groups will come up with some version of this. Okay, so now the second part of this. So now, the first part, we talked about the modules, the components. But now here we're going to look at when we're putting those all together. You know, remember I mentioned model-based systems engineering. We're using aspects of that, not full MBSE. And you see the term digital twin. So we wanted to take that whole thing and have it swappable when built, when integrated. We wanted to be able to have that whole model run as if it's the hardware. Of course, it's going to run at a lower bandwidth, at lower data rates. And then we can swap that with the actual hardware. And so the benefit of that is it allows us to do testing of the interfaces, testing of the IP before we built the FPGA. Right? Remember early on I talked about the FPGA challenges, the long compile times. This was done to mitigate that because we know that that's a problem. That shouldn't be a surprise. We say, hey, it's taking a long time to compile. So this is it's a system view. I'll zoom in on the part that's probably most critical, PowerPoint. So we see kind of like right there, we see the FPGA in the model, and that's all swappable. And you see like a recording of files. You know, this was recording to up to really high data rates. So that's why we were using TDMS files, and each of these are different channels. The user has the ability to choose multiple channels. They also wanted to have the ability to add more cards. So that's why earlier here you saw that we did use the actor framework on the software side. I think another key point to mention is that when you're building an FPGA system, software architecture sometimes gets put aside because we're so focused on the long compile times and all those challenges. But software architecture is really a critical part of it. Because you can build this really high-performing FPGA, but now they want to use it on many cards. Now we have to go and there's a lot of, essentially, there can be a lot of technical debt if we don't think this through. And then this shows the, generally the actor call chain hierarchy. And the reason you see there's two, all of the two at the bottom are all kind of like model and FPGA. So they're all, that's how we swap those. So we designed it so that way they could be swappable. So, we're able to test it. We're able to test it before the FPGA was finished. But then at some point, let's say that when they're finished and they want to make a change, they can put that change into the simulated part, verify it, and then flow it down. Okay. So here we have, I'm going to start to move a bit. I know we're on time here, running short on time. So digital product tester. So this is let's look at the excerpt first. So they've got a lot of requirements, like 350 requirements, and they need to be able to support them all. And so that's a lot of requirements. There's some risk with the compile times. And so, of course, we wrote a test plan for it, just to understand what those requirements, like how we're going to verify, right? A test of a good requirement is how it can be tested, if we know that we can test it. And we were able to have simulated tests for up to, something like 70 or 75% of the tests. So we got as much coverage as we could. And originally they wanted to send us like hardware and a whole bunch of setup and buy new hardware for us to like develop on. But what this allowed us to do is to do a lot of that without them even forget the lead time of the hardware, the costs of the hardware, the risks of setting up all that hardware, right? All these other hidden things. Murphy's Law basically, right? We're reducing that. And the good thing was that because it was, we also had a high pass rate when these were running with hardware. So to kind of zoom in here to give you a sense. So we got these requirements. And you see what we do is we first stay in this first section here. We want to make sure that we're simulating and testing these requirements. We're not even building hardware. We're compiling. And then at some point we go out here to do our hardware test, and then we're done. I don't know if this is I think this is the last case study. So now here, this one was as a group that's developing. They're developing IP, and the IP is not in LabVIEW FPGA, so it's a VHDL, let's say, and they're using NI as the hardware test platform to test out the IP, to run it on there. And they were looking for what's the best way to approach this, right? Because there's many different ways, and documentation will tell you what to do, what you can do, but how do you make that decision? So we worked with them to review the different types of workflows. So we mentioned like number 2, for example, Vivado export. Simulation export is something else that's also in LabVIEW that actually goes out to supported like a Xilinx simulator. And then simulation I/O is the built-in one to LabVIEW FPGA. And as a result, I'll show you the table where we did the analysis, I guess. So the company, this group had a lot of test engineers, but 1 or 2 firmware engineers. And we found that the other workflows required that firmware engineer. And for smaller changes or for updates, right? They wanted to, that person's available, but they wanted to be able to have it where it's it's a documented workflow, and then the test engineers, they can reliably, and this is kind of a standardized approach to that as well. So and we even tried it out. Like we tried a couple of use cases. We're like, okay, the firmware engineer wrote some IP, we put it in there, they tested it, they saw that it was working, the test engineers, and then he made another change. And then they saw that how they were able to put that in there, right? And it was because we documented that. If you ever use the IP integration node or the clip, there's all these wizards that you go through. And I would consider it a best practice to document all this. Like typically we take screenshots. I know it's not like a slick way of doing it, but we'll take screenshots of all the settings that we put in there, and that is essentially the procedure. So that way when you're going back in there and rerunning it, you're not setting a clock the wrong way or a data type the wrong way. You're setting it the same way each time. So yeah, so now the changes could be done by any of their test engineers. The last one, I think it's the last one. So here we had existing IP. They had LabVIEW FPGA, they had IP that was running through a clip. And specifically in this case, it was Verilog. And the LabVIEW FPGA had excess interface logic. So that meant that whenever the Verilog code changed to go into LabVIEW FPGA and reintegrate it into the clip, that would take a long time. So it was very painful, right? So we certainly saw that. And if you've heard of what an ICD is, an interface control document, we essentially defined the interface. We said, okay, these are the things that the Verilog needs. So and not only did we define it, but we made a similar diagram that what you saw earlier, and we found parts of the LabVIEW FPGA code that we saw that, hey, we could just put that into the Verilog, right? Since the program is using Verilog, we don't need to compete between the two approaches, right? They could both be in there. Some things to review on these case studies, I would say include, notice that in the first one, it was all purely like LabVIEW FPGA, some Xilinx IP. Whereas in the others, we used integration of IP with NI's simulation. And then you see in the last one, where we chose to not use, right, this last one here, we in fact simplified the LabVIEW FPGA. We reduced the things in the LabVIEW FPGA side and moved that all into the Verilog. So it's not always like, hey, always do this or always do that, right? We got to see like what's simpler, what's more efficient for the program. Okay, so trends. There's our crystal ball moment here. So some things on the NI side that I've seen as someone that's consulting users. I know that, if, like say 10 years ago, it was the majority were LabVIEW and LabVIEW FPGA users, right? They were purely working within that environment, whereas now we see a lot more companies and organizations. I'll go in and consult or train, and I'll see, here's the LabVIEW people, here's the test engineers, and here's the firmware team. So that's used to be the exception. It's becoming, again, I'm not going to guess at numbers, but it's becoming more common. So I used a similar format here. So we say that's the scenario. The proposed action, as we saw in the one with the clip simplification, it's really important when you have more people involved. It's LabVIEW FPGA, but you've got this clip or this other thing. That's a subsystem. So it's really important to understand what the interfaces are going to be between that. And there is a formal type of document for that. There's an interface control document that gets created that establishes that. So it's almost like a technical contract between this team and this team, and they say, this is how we're going to communicate from my system to yours. And if we understand that up front, right, that shouldn't be a surprise. That does reduce the integration risk. And of course, another benefit here is that we can have more access to IP, whether it's open source or licensed, or we have in-house developed. Right, it just gives you more flexibility because a lot of these companies will have IP already built. Right, so why redesign that? In the product picture earlier, whether it's an analog device, analog input or output, or whether it's a high-speed serial device, you see that there's a lot more high-speed serial, that's the HSS, or MGT, multi-gigabit transceiver interfacing on the products. I don't want to say that all of the new ones have high-speed serial ports, but all that I see have it. And so it's becoming near ubiquitous, right? It's in a lot of the products. It's a way of being able to move data in and out of these cards. So it's just everywhere. So it's almost like every product. I know that NI has like a high-speed serial product line, but in a sense, all, if not most of their FPGA products are essentially high-speed serial products. So I think the proposed action there is to have more tooling and examples that can help a user that's going to need that at some point, right? Like for example, the 5785 is an IF transceiver, so it's mainly for the analog inputs and outputs, but it also has a high-speed serial on there. That's a whole other project within the project. And of course, that sounds sales-ish. I guess the forecast is more NI FPGA cards in lots of systems. And of course, a better developer experience. Certainly that's not the goal, but I think the idea is that if the tools are in the products are a fit, you want to be able to integrate them. So that is something that I think is more than a trend. CI/CD in NI FPGA workflows. I don't see it a lot, but it's definitely happening, right? You're seeing people saying, hey, I'd like to have run things on AWS, or run things in Jenkins or Bamboo, or whatever the tool of choice is, the DevOps or the pipelines, all those CI/CD things. So to be able to automate those workflows. And I think that's the same thing as the previous one. That's development of tooling. There are some functions that LabVIEW FPGA has for this. They're in the specific, it's in one of the vi.lib folders, but getting just some more examples built out for those, I think, is the proposed action there. And if you have, for the first project that I showed you, we did do a build out of that. We did have some nightly builds. I didn't mention that, because again, there's not enough time for all that. And we did do that. Varied host interface languages for NI FPGA is another thing that we're seeing. So you make a LabVIEW FPGA, you have LabVIEW on the Windows side and the LabVIEW FPGA and the hardware. There's a C API that NI makes. The C API can work with C and C#. The C API has been wrapped into a Python interface. So that's becoming more a thing. Many years ago, NI was able to support Linux for some of their FPGA products, so different OSs, right? So it's not just Windows and LabVIEW, that's on the host side. And the proposed action here, because I think that the functions exist for it, my observation, the proposed action here is to have advocating, what do we mean by advocating of best practices? So people see, well, I'm going to use Python for my interface. They think that they can skip a whole bunch of steps, whereas they still need to do some kind of LabVIEW host development to make a test bench, to test out the FPGA part. And then, because they now know the interface, call that in Python, or whatever language you need to call it in, whatever OS you need. But that other part, where you're testing it out and confirming it, currently is best done within the LabVIEW environment. So even if you're not planning to deploy with that is, so I don't think that's really, that best practice in the workflow has not really been, it needs to be advocated. So we get more accessible for developers, development teams have, it's more of a mixed background, in the development team. So you want to be able to have access, those users to be able to write software for that, different environments. So now FPGA trends, taking a step back, right? We started out broad We went specific to NI, and now we kind of like looked at NI's kind of like FPGA, some trends. Now I'm gonna look at just in general, what do we see in the FPGA world? Well, the chips are getting, there's a thing called Moore's Law, which is really just an observation that things are happening. But we know semiconductors just keep getting bigger and better, and they can do more things. And a specific example of that is what's called a system on chip. System on chips don't have a formal definition, but the minute it has more than one type of thing, maybe we can call that a system on chip. Now, the name system on chip, I don't think is accidental, but if you have a system on chip, the team that's developing it is probably gonna look at it as a system. You can't just have like that one person, right? Maybe it's getting too complex for that one person, as it's typically done, to do all the FPGA development or it's funny, I mentioned the word FPGA. If you look at a lot of the newer data sheets, you won't even see the word gates in there anymore, in fact, right? We still just call them FPGAs, just for continuity. But certainly the proposed action here is systems engineering, right? Some of this, some of the workflows I talked about. And of course, some of the software engineering techniques, right? These things exist. CI/CD and the source code control, these things do exist on the software side, very mature. And so they do need to be brought in. And then these larger teams, once you start to grow the team, they will need that structure. Some kind of structure is needed. And the tools could support that. And just to kind of give you an example, this is like from the Xilinx website. You kind of see that you've got, RF on, not just digital components inside of an FPGA. You now have RF. You have analog digital converters, digital to analog converters, CPUs, GPUs. There's a video codec in there. It's there you go here. Versal. It's got the AI engines, network on chip. That's sure speaks to complexity of this. What used to just be like a couple of gates. And I think this is my last one. So now one thing we do see is that data centers, there's LLMs, and I had to include something about LLMs in this presentation, right? It's like I got to check that box. They're using a lot of CPUs and GPUs, and while they have that flexibility that we saw earlier, they use a lot of power. Power per consumption, it's almost like power used per calculation is very high on those. And with an FPGA, you can manage that because you can make your own data types. You can get really specific with that. And so that's something that, putting data centers everywhere, but the FPGA, and it already is happening, right? I talk about this as a trend. Certainly this has been observed. It's happening already. Okay. Sorry, I didn't leave a lot of time for questions, but I will be around. I'm not going to any other, I don't know where I'm going after this, but you can ask questions. Thank you for coming.